Hi there, my name's Craig Weightman and I'm Senior Lecturer in Games Programming at University of Staffordshire.
And I'm Mike Acosta, I'm Senior Lecturer and Course Leader for Games Art at the University of Staffordshire.
Yeah. Okay, so what we're going to be talking about today, essentially, is the mathematics of prediction in games. Maths is such a fundamental part of programming, computer science, and everything that sort of underpins games, graphics, physics, all that kind of stuff. And so what we're going to be discussing today is some of the kinds of maths that's useful. So one of the things that we're going to have a look at is we're going to be looking at the mathematics concepts that we're going to be talking about today. We're going to start off with lines. So you're familiar with lines, aren't you?
Yeah, I can draw lines.
Yeah, you can draw lines. This is good, but can you? I've got a question for you.
So we'll just put that out there that
you can do
I'm an artist,
yeah.
and so
you can draw lines.
I can draw lines, but also what we're talking about today is something that's slightly alien to me.
Yeah.
So great for those of you who are looking to get into this kind of thing and come to Staffordshire University and be taught by the likes of Craig. So this is the kind of teaching you can expect.
Yep. Well, yeah. So yeah, we're going to be talking about lines, and I do have a question for you. As you believe you draw lines, so
Okay.
So there's one question that's out there, and you're thinking, what's he going to ask me? So I'm going to discuss some usage. So we're going to talk about how maths can be used for prediction. In particular, we're talking about physics, and also we're going to be talking about multiplayer games, because physics is a simulation. That's what we do with games, right? So it's really important that objects that we have in what's effectively a simulated environment, they respond well. They do stuff that we expect them to do in a physical world, right? So my question to you is, first question to you, perhaps only question.
I didn't know there were questions.
Well, no, it's a good surprise though, isn't it?
Yeah, thanks.
So,
do you know the question?
I do. I'm trying to phrase this. So you think you've drawn a line? I can tell you haven't drawn a line. Ever in your life. Do you know why?
Why?
Because it's impossible. You know, because mathematically speaking, you have been drawing line segments.
Okay.
All your life, right? Okay. because what a line is, mathematically speaking, and it's kind of like an important distinction, only because of what we're going to be talking about today. Infinite. So you'll have, don't worry, yeah, indeed, yeah.
Okay.
So you know, to all intents and purposes, you have been drawing lines. So you know, yeah, hopefully you don't have some kind of thing. Oh, what's my life been all about? But no, so you have been drawing lines, but we're talking about infinite lines, so infinite quantities. So we're starting off with lines because it's the basics behind prediction, particularly with prediction of motion and paths and that kind of stuff.
Okay.
So we're starting off with lines. We'll move on to things like curves and that kind of stuff and talk about, because the maths gets a bit more intense, and so therefore is probably a little bit beyond the scope of this as well, but it gives...
And beyond the scope of me.
A little bit. Don't worry, you look panicked.
I am panicked.
It's fine.
Oh, wait, it's a maths question.
Yeah, no, I'm not going to ask a maths question.
Right.
So, yeah, let's get into this. Let's just start with the information that you need. So, the first thing you need for a line is coordinate. Panic look. It's a coordinate. Well done. That's it. So we're going to talk in general here. We've got X, Y, and Z. So in terms of values, you know, this is general stuff. Yeah. So you need a point in space, and we've got working on a 2D space here. So we've got X, Y, and Z, and that's a coordinate. But we imagine that it's, you know, Z is 0 effectively because we're talking about 2 dimensions. And let's give ourselves an axis because it's a lot easier to talk about these kinds of things, right? Okay, so we have that, and what we need, actually, we need 2 pieces of information to represent a line in maths, and what we're going to do is we're going to derive 2 things. One thing is we're going to take a line, and we're going to create what's called a linear equation of the line. Okay? And what it will effectively do, it will allow us to be able to trace up and down the line at any given moment, so that we will know where this dot can be, only restricted on that line in space. And from that, from that linear equation of the line, we can derive something called parametric equations, where we can just change the values in order to get what that other position is going to be. Okay. Does that sort of make sense?
Yeah.
Yep. So we need two pieces of information. We've got a point in space, and we also have some line, and that line is going in a particular direction. Okay, so we need a direction. We'll talk about direction a little bit later, but we've got some point that it passes through, and we've got this basically infinite line that passes from one side to the other. So it's going that way, right? Okay, so we're also going to produce another position, because what we need to do is we need to create some sort of vectors that sort of point to these dots here, and relate some of the mathematics in order to find this linear equation. Okay, so what we're going to do, and we've got down here, we've got these. We've called this point 0. This is your initial origin position, and we've got this position 1. And down here, as in most graphs, you've got an origin point. Okay, so what we can do is we can represent these points as vectors. Okay, so effectively what we have is we've got these two vector points which are coming from the origin, and they end at these particular coordinates here. Okay, and the way these are connected is that in order to, if you start off with this first arrow here, which is pointing to our first coordinate here, we can derive this one, right, by adding a third vector. Okay, and we're calling that d because it's the distance between them. Okay, so if you were to take this coordinate here and take it away from this coordinate here, we would have that. Okay. Okay.
Yep.
And so what can we do there? So we can talk about a triangle law, which is essentially an addition law for vectors. Okay, so we have this, and that's sort of like this is where the math starts. Okay, so we've got what we've essentially got here is that we've got some new position, and that could be any position. I've just put it out there. Yeah, no, put it in there. But that's your original position plus that vector, that distance. Yeah. Okay. 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 So what we don't want is we've got a vector here which is a combination of direction and magnitude. So if you've ever seen sort of like Despicable Me, you know that villain vector. He's got direction and magnitude, right? So that's what vectors are, right? Okay. So what we want to do is we want to strip out the magnitude, right? And what we do is we call it normalization of a vector. Okay. So you've worked with normals before. You've worked on lighting and that kind of stuff. Yeah. So these are normal vectors. So usually what you'd have is if you've got a flat surface like this table, as you're aware, is that you can basically do something called a cross product on two vectors, and it essentially creates a third vector that's 90 degrees to the other two. And that, you can use that as a normal, and if you normalize it, you can use that for lighting and all sorts of different things. We use it we use it for lightings, we use it for collisions, we do all those kinds of things when we're doing the programming. So we use this quite a lot. So we need to normalize that, and so I've changed that D to direction, and it's all going to become direction, because all we do by stripping out that magnitude, we basically only retain the directional information. So it's a vector that is normalized. Its magnitude is reduced to 1, and therefore can be multiplied by anything to put a magnitude back in. Okay. Right? So what we want to do with this, if we're plotting from 0 to any point on this line, or even this way, what we want to do is proportionate to as time passes, which is what it's going to end up doing, we're going to put that magnitude back in. So it's still in that direction, it's just now it's pointing there, or it's pointing here, or it's pointing here. Okay. We do that by manipulating that magnitude, but we have to strip it out first. So mathematically, that looks like this. Okay, so what that basically says is that this direction is your vector, which was your original vector d, and this bit of notation here is the magnitude of vector d. Okay, so if we were to sort of expand that out, it's basically, you might have seen this, back in the days of sort of like GCSE maths, that kind of stuff. That's Pythagoras theorem, right? So the idea of a magnitude of a vector, if you imagine that as a triangle, sort of like a hypotenuse, the square on the hypotenuse is equal to the sum of the squares of the other two sides, right? Yeah. So that's the magnitude. But it works. It doesn't matter how many effectively sides of that triangle we've got. It still works for 3D space. We could put an extra letter in there. It would still work, right? Okay. So we're adding those squares together. So x squared plus y squared plus z squared. Square root of that will give you a single value, which is the length of the vector, or the magnitude. And what we do is we take each of these terms, x, y, and z, and we divide each of them by that value. Okay. And we end up with a normalized vector, which has just the length stripped out of it, right? And this is arguably not 1 when in comparison with everything else. I just wanted to represent that it's shortened, right? Okay, so we've just got this directional vector. So what can we do with that? Well, we can sort of put that back in. Like, we can now assume that D, whereas D's been stripped down to just its pure direction, we can say that the original D, which we're still calling direction, but we're timesing it, because remember, the magnitude is now 1. Mm-hmm. If we multiply that vector by anything, so say if we multiplied it by, I don't know, 30, the magnitude would be 30, right? So, you know, that, arguably. I'm with you there. Yeah. So your D, which we put back in there, is now called direction times T. T is representing time.
Thought so.
So that, there you go. See? Excellent.
I was going to say it out loud, but I didn't want to guess I was wrong.
Yeah. Oh, it's not going to be T.
No,
right?
good.
It's going to be T.
Yeah.
Or even T. No. So it's going to be time. So we've got we've still got the same formula. It's just that we've done some stuff to it. Yeah. What we've done is we've turned this original vector into direction times T. So we've still got the direction information. It's just now we can put in any magnitude we like. Okay. So,
I'm kind of picturing this, by the way, in my head as like you're a player.
Yes,
and
absolutely.
You're here, and then you want to get to there, and this is the equation for doing so.
We want to exactly.
But at the minute, we're at a single pace.
Yeah,
is that right?
We are at a single pace because what generally happens with vectors is that we would use velocity, for instance. Yeah. So velocity is a vector because it has a magnitude, which is speed, and it has a direction. Yeah. You can change velocity by keeping the speed and just changing the direction. Okay. Or you can keep the direction and change the speed. That's also a change of velocity, right?
Is that what's coming up next?
Well, it's getting there. Yeah, okay. We are getting there. Okay. So yeah, I actually tie this in when I start. I've done a snippet of some of the code from a physics framework that we use for the students. So I can sort of give it some sort of context. Cool. All right. So we do have that. And what this is, by the way, this is called a linear equation of the line, and it could be any line because all you need, remember, is some position in space and some direction. Okay. Yeah. Any line. Yeah. So this is a linear equation of the line. So what that translates to is, and there's a little bit of notation here, when it comes to normalized vectors, they tend to use IJK notation. Okay, some multiple of I, J, or K. Okay, it doesn't necessarily matter what those values particularly are. But what we've done is we've taken these values here for P0, just here, it's the same equation, and we've got direction I, J, and K, which is just the normalized vector, and we're just multiplying it by T. Okay? We're going to expand it out. So each of these things, basically it becomes this. So it's it's the original position plus each of these terms multiplied by T. I times T, J times T, K times T. Yep. Right? Okay. And then we can expand it out a little bit further just to finalize it so that we can have your final sort of vector, as it were, is that we can go x0, so that little component there, plus I times T, y0 plus J times T, and z0 plus K times T. Right? So they're so what that basically means is this on the next slide. What we can do is we can create something called what are called parametric equations. These have all been, it's almost like what we've done is we can take each of these common values here, and we basically rip them out to make something called parametric equations. Okay? So we can create, say, x1, as it's highlighted up here, is x0 plus I times t. So I is from the direction. And then similarly, the new y is going to be your original y plus j times t. And the new z is going to be old z plus k times t, right?
Okay.
And so what does that mean? Well, we can trace this. So if some value t1, I don't know, 3 seconds, right? We don't do things necessarily in seconds. I'll explain that later. But we've got t1, which is 3 seconds. So we can multiply all that out, right?
Yeah.
And we can say another position on that line, say t2. It's the same set of equations, just a different value that we're multiplying by.
Yeah.
So all we're doing is you can imagine a line here. So that's one vector between p0 and t1, p0 and t2, p0 and t3. We're adding that magnitude back in.
Yeah.
Right. So and even if you wanted to go the other side, so back down the line from p0, it would be a negative t value, and you would be able to see where it's been if you're going at this one particular speed. So what essentially happens is that we're using these kinds of equations all the time, and one of the things that this kind of maths goes into is what's known as dead reckoning. Okay, so dead reckoning is something whereby probably not personally, but in a game, say, and you want to fire a rocket at somebody, right, and they're just following along, and they're running down, and you said they're going to be over there, and you'll fire at that position, and they cross each other at that moment. Yeah. I mean, typically it doesn't necessarily happen in all games, but in real life, that's definitely what you need to consider.
If they're running in a straight line, my brains are doing that math by itself, and going, I need to shoot here, because he's going to end up there.
And you're doing it with your imagination and visually and all that kind of stuff.
Whereas the software's doing this.
Whereas the software is doing this.
Cool.
Right. Okay. So, it becomes important in terms of prediction. Right, because you're having to predict where things are, and there's some interesting necessary usages that we have. Okay.
Yeah. So at time 3 on a straight line, he's going to be there.
Yeah, that's right.
Got it.
And so an AI, you could have a cannon in a game that's run by some kind of AI that's going to calculate. There's a time for your weapon to get to a target, and it's not just raycast. They're not just going to fall over. You've got that physics in there. Then the AI sort of controlled NPC cannon could go, right, I'm going to fire over there. You have to code in some of the errors in there and then take them out unless you change direction or something like that, right?
Or slow down.
Or speed up. Yeah, exactly. Yeah.
Okay.
So this is the important sort of math, and it's all called dead reckoning. There's a fair few sort of prediction sort of things that we come in.
I dead reckon he's going to be there.
Yeah, that's it. I dead reckon. You know what? I dead reckon he's going to be there.
He's going to be right there.
That's it. Yeah, that's it. Yeah,
okay.
That's essentially it. So there's some interesting stuff that comes out of this, because physics, like I said previously, is that physics is all about simulating a world or the world, right? So you'd expect the kinds of physics that we get in the real world to be reflected some way in games, depending on their, how well they've been coded and how well they've been put together. Right?
Yeah. You'd hope so.
Well, you'd hope so, and it's pretty good. But because here at University of Staffordshire, when we're doing sort of the programming kind of things, and we've got second years that are coming up with cloth physics, real-time calculated cloth physics, which works on this kind of stuff. I've just seen a recent hand-in that's got basically a trampoline net, right? And he creates this ball in this world, and this is all coded from the ground up, right, by the way. So what we're trying to teach students from the programming perspective is that yes, you can use Unity, yes, you can use Unreal or whatever, or whatever, But we then go, okay, well, what can you do from the ground up? Let's code it. Let's code the graphics from the ground up. Let's code the physics from the ground up and put an interface over there. Mm-hmm. And you've got a physics graphics engine that you can create a game in, right? So this is what we do. It's all from C++ code upwards, right? So, like I said, this guy, we've got this ball that's just been dropped in this net, and you can see the net, so the points in the net sort of moving because of the movement of the ball inside it, and it settles at the bottom because of gravity and all that kind of stuff. And all of this, it's crazy, and it's all real time.
It reminds me of the guys at Pixar when they had to plot. You know, they didn't have software that we have now and be able to see visibly what things were doing, so they were plotting coordinates on a graph in order to like make hands move. Like that.
It's that kind of stuff. So hands move. That's something called inverse kinematics and forward kinematics, and there's loads of maths behind that as well. So it's interesting stuff. And this guy is like throwing all these different weights into this net, and it's getting heavier and heavier. And he's even got it coded to tear. When it tears, all the things are going like everywhere.
Wow.
It's crazy.
That's cool.
It's crazy. So lots of fun, lots of hard work, but at the end you get some really satisfying results out of this kind of stuff. So what have we got here? Let's get back to this. So what we've got here is we've got a vector 3 position.
You've got to have some pretty good outtakes of that sort of stuff as you're designing these things.
Yeah, absolutely. Yeah.
They go wrong.
Yeah, they do. Yeah. I mean, you can get some really. Well, I could talk about how things can go wrong with this little thing here, delta time, right? So we've got a vector 3 position, and that's essentially getting a transform, which is the ability to move something around in position and that kind of stuff. And so it gets a position, and here we've got some physics calculations, right? So what we're doing is we're predicting where something should be under particular forces. Okay. So we can take sort of like your net force when you're moving around inside a game. You've got thrust moving forwards. You've got gravity pulling you down constantly. Mm-hmm. You've got potentially wind. So those games where I'm pretty fond of the sort of Jedi Star Wars games where you see some wind blowing out of a vent at some point, and you can just like jump into it and it blows you up. Yeah. But that is your forward momentum. That's one force, so you're adding that force to something called a net force. So it's plus equals. That's for the acceleration. But we can add this net force. It's just one vector.
You wanted to get the word force into this.
The force. We're very much using the force all the time.
Star Wars fan, Craig.
I am a big Star Wars fan. That's true. Yeah. So
minus like anything that's restricting that.
Yeah,
like
if you've got
friction and gravity.
All of it, because you've got your forward momentum, which is your force, not necessarily momentum, but we've got your forward force. You push forward on your controller, you're moving forwards. Mm-hmm. You've got gravity keeping you downwards. That's added. That's two vectors added together into one force. We can throw if you're going along on wheels, or you're sliding along or something like that. You've got drag, which is another vector force going in the opposite direction, added to what's already in there. Yeah. So you're adding all these vector forces together, and it's something called D'Alembert's principle, right? So it's called D'Alembert's principle. Mm-hmm. It basically states there is only really one force pointing you towards your next position, and that's made out of all the different forces that are acting on you right now, all added together into one vector, which has a magnitude and a direction for the next tick of the clock. Okay. And this is where we come into here. So we've got acceleration, so that's all of your forces, your singular added together force, divided by your mass, okay? Mm-hmm. So that's your acceleration. Then we can use that acceleration, so that's essentially new velocity is current velocity plus new acceleration times time. Mm-hmm. So you can see here, we've got a value here, which is basically sort of like a magnitude kind of thing. So the acceleration is a vector, but that's multiplied by time, just like we've seen previously. And then we can take that velocity times your delta time, and I'll talk about this delta time in a bit. That's a new position. So this delta time is calculated around about 60 frames per second.
Okay.
So when we set up a physics framework, we set up our time step so that everything happens within a tick of this delta time. So that's delta time is the time since the last frame.
Okay.
Okay? So that's usually about 16.67 milliseconds, right? So what that basically means is there's a new position is updated every 16.67 milliseconds.
Okay. Yeah, okay, I'm with you.
So now...
So if someone, let me go back to the game that we're imaginarily playing, and we're trying to get the guy who's running forward. You're saying that the software is updating his position at every 16 milliseconds?
Yeah. Yeah.
Okay.
Yeah. So it happens quite quick, and these are the things that can go wrong. If you get these what's called time steps wrong, or they're too big, you can get massive errors. So you can get spring physics, and you can have springs just acting all out of control when they're not supposed to, because we live in a world that is fairly continuous, unless you're going to go down right into the atomic sort of particle level, but a game is frame based. It's discrete. So you update a frame, you draw the next frame. All of the calculations for physics have to be calculated. Where's everything going to be in the next frame? Okay. And then it draws it.
Okay.
Right. So all of this sort of needs to be done. So we set that position. We calculate a position from all of this, and we send that position to set position on whatever object that's attached to. Okay. And so that means that we don't have to stick to lines anymore, because remember, this net force is going to be pointing that way or this way in that given instance.
Yeah.
And so it could be starting to move in a curve, and because we're working at 16.67 milliseconds, you can predict where it should be for the next draw.
I actually get it.
Yeah? Yeah, that's cool. That's good. I'm glad I'm doing my job.
Yeah.
Yeah. Okay, so that's physics. And we do that all the time, and it's great. I love sort of, the maths of it is important to learn, and we do go into what we tend to do with these kinds of things, physics and multiplayer stuff and all that kind of stuff. We do have lectures on the actual maths behind it, because then when we go into the tutorials and it's going, okay, code this within this massive code base, which is could be a framework for physics, for instance, because these things they're big. They involve a lot of stuff. Physics needs your graphics set up and everything like that through DirectX and that kind of thing, and then we'll code the physics into it. So it's quite a big sort of deal. But we learn, we teach the various maths that goes into it, and we actually get students daring to go further, and it's really, really good. Yeah. So the other thing is, I've talked about curved paths there, and I'm going to talk about how things get slightly more advanced. So we've got our various T positions, okay, and we've got where.
Did you draw that?
I didn't draw that. No, I stole that.
I was thinking about bouncing balls, and it should be stretched a little bit on its way up.
Yeah, no, yeah. Of course, you're stretching deformation. It's your animation coming into that. Yeah, we could do that, but it'd take a lot more maths.
Yeah.
Okay, but that's a drawing anyway. So we've got that. We've got basically we've got position. We've got an arrow. Where's it going? So that's going to lead over to here. At time 2, it was taken to here, and it slightly changed its vector. It's going this way now, and at here it started going towards there. So you can see it's probably it's under the influence of some force.
Yeah.
Right.
Yeah. Distance is getting shorter, and
yeah, exactly. So it's going that way, and it's coming downwards. And the thing is, where is it supposed to be? It's on a curved line, right? So in the linear equation, we've got this straight line, right? And for curved paths, we can use various things. So what we've got here is this velocity at it's sort of like current time plus delta. Now this is mathematical notation that you get everywhere. It's this triangle, which is capital delta from the Greek alphabet, and what it essentially means is a small change in time.
Okay.
Okay, so we've got current time plus
small change
tinsy change in time. Let's call it 16.67 milliseconds.
Okay.
Right? So
works for us.
It's literally delta time.
Okay.
Yeah?
Okay, yeah.
So, So all of that is equal to your velocity at this time step, as it is now, plus the acceleration at this time step multiplied by delta time, and that becomes this. And we can then feed that into S here, which is a position that uses this calculation, plugs it in here, but it's your current position plus velocity times delta time, which is what you saw in that snippet of code before, right?
Yeah.
And this is what's known as, it's an explicit Euler integrator, right? That's what that's called.
Euler, that's how you pronounce it?
Yes. But lots of people pronounce it as Euler. It's actually Euler, right? Okay. And Euler did loads and loads of mathematical stuff. So he's done stuff to do with rotations. So any rotations have been used. You can use Euler for rotations, but we use something else called quaternions, which is a whole different basis of maths.
I've seen that as well. It's in the sort of the rigging and animation side of things. I see both those terms. Is it to do with like its sort of local position compared to like wall position and things like that, or not?
What it is, it's about
going off piece.
No, it's fine because it is all about prediction, because it is rotation. If something is rotating, if you've got force coming into something, and it's not force, it's called torque. So you like your cars, don't you? Yeah. So you're into your torque and that kind of stuff. But torque applied to a particular position, and then we can get it rotating, and we can get into things like inertia and inertia tensors, which is a resistance, which is different for different axes for rotation, right? Okay. But with there's a problem, is that what happens is that you can take a ball and you can rotate it around X, you can rotate it around Y, and you rotate it around Z, and there's your new position. There's a problem though, because we are getting a bit off piste here, but there's a problem with Euler integration, Euler rotation, because you can have something called gimbal lock. And what happens there is where you've got two axes that are frozen. So you lose a degree of movement. Okay. And it happens in space all the time. So they have to, if two axes lock for a satellite, it means that you can't rotate properly, and it spins out of control. And that's happened quite a lot. In lectures, I give examples of NASA that have had these problems, and they've had to fight these kinds of things. Yeah, but the other rotation thing is quaternions. So quaternions is basically almost like it's a way of representing using a four-dimensional number. Okay, I'm not going to get into that.
We don't need to do this.
No. I'm not going to get into that, no.
You don't need another dimension.
No, you don't need another dimension. It's using a four-dimensional number, would you believe? And we use some mathematics that's borrowed from something called complex numbers, where you can do multiplications and divisions, and they work properly in 3D space with vectors, which you couldn't do without quaternions. And we do that to rotate. And they're actually gimbal lock free, so you don't lock those axes when they're rotating.
This guy's good.
I try to be. Anyway, so we've got all that kind of stuff. But there's more maths, but I'm just going to go to the semi-implicit Euler. So I feel like I'm selling you different kinds of maths. So you could go. There's problems with this. The explicit Euler is that if your time step's too big, you can have issues.
Okay.
So therefore, there are more ways of doing things. So another one we could talk about is the semi-implicit Euler, which is slightly tweaked because this is using acceleration, and it's different from this in this kind of way. So we're using this velocity term and multiplying that whole term by this delta time in order to get an update of position. And it's what you can do. For instance, if you were to predict what's called a simple harmonic oscillator. So if you've got something bouncing up and down with a fixed point like this, with an explicit Euler integrator, you will end up, you can get it so that it's sort of like the energy's increasing. So it's getting bigger, right? But just by changing the math slightly, you can actually get it match how it's supposed to be. And there's other ways of doing it. I mean, it's about there's something called Verlet integration. Verlet, you may have heard it in terms of cloth physics, that kind of stuff. It's the kind of maths that's used for those nice sort of blowing in the wind kind of things that are represented in games. That's basically how a cloth is made up of vertices, right? Mm-hmm. And each of those vertices are points, and they're all connected by, we can model springs, okay? Mm-hmm. And so as each of those points move, they constrain each other.
Okay. So
as they move, it moves everything else up to a certain distance, all right? Mm-hmm. So you get that nice sort of thing. And Verlet integration is for the prediction of that kind of stuff. Okay. You know, and all that kind of thing, and you can use it in different kinds of maths in predicting how fluids should move and that kind of stuff. So it's all pretty cool. It's cool stuff, and then we can get onto things like RK4. Anyway, there's lots of maths. It gets more complicated, but the thing is, what we can do is, what's a great way about programming and using vector maths and linear maths and all that kind of stuff is that you can visualize kind of as it works, because as you program it, it's kind of expressed in a different format to all of these symbols and all that kind of stuff in order to make it work, in order to update stuff in the code. And so you get a better grasp of what maths is and how it actually works by coding, right? And coding this kind of stuff into mm-hmm. it. But yeah, the other thing is that I said we'd mention is that in multiplayer games. Now then, you like playing your multiplayer games? Get time to play multiplayer games? You've got kids now?
Not as much time.
so no, I don't. Yeah.
But I have done in the past, yeah.
Yeah, well, we've played them together as well, haven't we? So.
And I have noticed for lag, which is
exactly.
Is this going wrong, right?
Exactly.
Okay.
Yeah. So there's lag, and so what happens is that when you're playing a multiplayer game, everybody playing that game, say you're playing F1, right? Everybody playing that game is in their own little parallel game.
Yeah.
Yeah?
Yeah.
So that's sort of local to the machine that you're playing on. And what happens is, in order to synchronize all of that together, you need to send information. You need to send packets across the network, right? So everybody's position, everybody's velocity, what they're doing and all that kind of stuff all needs to be sent to a server, and if it's a server dominant hierarchical sort of multiplayer game, that then broadcasts it out to everybody that's in that game, and from their own perspectives they can see what's going on for these different objects.
Makes so much more sense now.
Yeah.
Really. Yeah. Like F1 is a perfect example. I used to play that a lot, and online a lot.
Yeah.
And you would see a car just going, boop, boop.
Yeah, it does, yeah, and that's the problem. That's actually a problem with prediction. If you haven't got your prediction correct, what can happen is, what happens every so often is that you'll get an update packet anyway, right? And it says, and it basically goes, this object, this information is associated with that car. Mm-hmm. This is its current in-game position. Mm-hmm. And it might have predicted into the wrong place.
Yeah.
Oh, there you go, it's updated now.
Because the millisecond that he got that information, the guy slammed the brakes on or something, and then it didn't get that. It put it over there.
Exactly. Okay. It's very, very difficult thing to do, because we're talking about things. People could be playing these games from all over the world, right? Yeah. And there's lag. You've got your network. You're competing with network traffic. You're competing with TikTok and Twitter and everybody else that ever uses the internet for everything, right? So these things get sent over the network, and so there's going to be lag. The more information you can send all the information if you want, but it's just going to be too big. There's going to be too much lag. You're going to hit bottlenecks in the physical structure of the internet.
So you have to send the predicted information.
You have to send the information that your local machine can predict. So information like that might be velocity, force information, that kind of stuff. So remember, forces have direction and magnitude. They update your position. But effectively, what you can do is, so long as you have the correct information, and everybody's sharing the same kind of environment and the same kind of physics, for a certain amount of time, you can predict where that's going to be. You're more likely to have errors as you move forward in time, as those delta times tick away, right?
Okay.
So what that means is that you could be playing your F1 game, and you're accelerating forwards or something like that. You don't have to be sending over the network packets. I'm going forwards, right? What you do is you go, I'm going forwards.
Yeah.
Okay, and everybody else is going, I see Mike going forwards.
Yeah.
You know, that's their representation of you.
Yeah.
And so when you change slightly, that's a new packet, new information.
Okay.
Yeah?
Okay. Or lift off the accelerator or brake.
Or lift off the accelerator or brake or anything like that. It's just
But if I just go that,
Mhm.
I'm going forwards.
Mhm.
It doesn't need any other information.
It doesn't need any other information until you change stuff. And actually, over all of that time, if you're thinking about 16.67 milliseconds, between 16 and 17 milliseconds, that's a lot of time, right? So you might be going down a straight for 3 seconds.
Yeah.
You don't have to send information for all that time, potentially,
Yeah.
because locally you can model that.
Yeah.
Yeah, and that's how everything sort of kind of works with multiplayer. So prediction and maths is fundamental to programming. It's fundamental to everything we do. It's fundamental to every game engine, physics and graphics and all that kind of stuff. It predicts how things should behave. And it even can be used for dead reckoning in multiplayer games, so that things can be behaving as they should without sending too much information that could potentially crash the network. And you can see, you could put it down to say, I don't know, that you know, Pong, when you've got that, that's the simplest way of thinking about it. When you've got the other paddle because you're playing someone else, that's your machine moving that up and down based on that one packet, right? But it's just more complicated thinking about it in terms of F1 or Fortnite or whatever it is, right? Okay, so yeah, that's where we're at. So that's why sort of like maths is so useful. So anybody thinking about, hopefully I haven't put people off doing games programming, because it's such a fascinating sort of topic. It does involve maths.
It really is fascinating, actually.
It really.
I just don't have a mathematical brain.
Wow.
But I love everything you've just been talking about.
Oh, thanks very much. Yeah, well, pleasure. I mean, I love talking about it. I love teaching about it. I love these kinds of concepts, and yeah, it's really good. So essentially, yeah, that's what we've done. We talked about physics. We've talked about multiplayer games. So yeah, if you want to learn more, come and learn more, because yeah, we love it. We'd love to have you. Yeah.
Indeed.
Okay.
Awesome.
Yep. Thank you very much. See you later.